Our next speaker is my wonderful office mate, Anna van Yperen from the University of Oslo, and she will give us a talk on Diachronous key stratigraphic surfaces in low accommodation fluvio-deltaic settings. So, Anna, whenever you want to go, you go for it.
All right. Well, thank you for the introduction. I am doing a postdoc at the University of Oslo, and this talk will be about some of the results of my PhD. So yeah, we'll talk about Diachronous key stratigraphic surfaces in low accommodation fluvio-deltaic settings, and I will take you to the US, which fits nicely this SEPM setting, I hope. So what I will address is basically how we can correlate between continental and shallow marine strata. So back in the days when the sequence boundary was considered a bypass surface, and it would basically represent a timeline separating older from younger strata everywhere. And there was a big debate about how to extend this sequence boundary into the marine realm. Was it below or above strata deposited during sea level fall? But during the last years, there's been an increased consensus that the sequence boundary is less of a timeline, so more composite and diachronous. But how would we correlate such a diachronous sequence boundary into a single surface? And well, this is me during my first fieldwork asking myself questions. But so why is this important? This is important because the accurate documentation and interpretation of regional scale stratigraphic surfaces is paramount to establish correlations between continental and shallow marine strata. And these regional scale stratigraphic surfaces are really important as they influence our understanding of the basin infill. I will give you a little teaser. Now you see that I placed here some numbers and they represent time steps. And I believe we should acknowledge that the fluvial deposits in the upstream are deposited throughout a relative sea level cycle, which makes their underlying surface composite and diachronous. And these fluvial strata is deposited at the same time as the shallow marine strata. Hence, we cannot have just one single correlative surface, but we need several. But first of all, I will introduce the study area. So we go to Northern America, to the Cretaceous, where temperatures were higher and sea level was higher. So the low-lying part of the continent was inundated by this western interior seaway, and there was a mountain chain in the west and many river systems flowing from these mountains into the seaway. And some of that is preserved. Lots of us, I think, know the excellent exposure of the well-known book cliffs, and some of the well-known formations are the Black Hawk and the Castlegate and the Yperen sandstone. But for my PhD, I studied the Dakota sandstone, which is a few million years older, but also one of these river to shallow marine systems. So if we zoom in a little more, we see that mountain chain here and then a schematic representation of the system. And this is the depot center of the delta. And then here in brown, you see the fluvial sandstone of the Dakota Group, which is further subdivided into in this part of the Western US. And I really focus on the Mesa Rica, but I mean, the names are not really that important. So the underlying shale that you see here relates to this first connection between the Boreal and Tethys Ocean. This square is New Mexico. And then we had a short regressive phase that caused deposition of these fluvial deposits. And then again, these shales belong to the more prolonged presence of the Western Interior Seaway. And as you can see, this profile runs more or less to the border of Colorado and New Mexico. And that was the work published before my PhD. And one of my tasks was basically to extend the profile. So we went to New Mexico and we managed to extend the profile. Now we also have the deltaic deposits here in yellow. And I do a little advertisement. We have a publication about the fully deltaic deposit development here in the center of the basin, and a one that goes into the details of individual mouth bars here at the proximal part of the basin. And then finally one that addresses the whole profile, which I will talk about now. So we zoom in a little more, Colorado and New Mexico, and all these dots are log localities, and in orange the ones that I collected during the PhD, with a focus here on the basin rim and the basin center. And then we integrated it with previously published data, and we also have some drone survey data here in dark green, which also focuses here on the basin rim and center. We did the usual facies analysis, grouped them into facies associations, identified channel types and key stratigraphic surfaces, and then we have this resulting profile, and the direction follows the average paleocurrent. But it has quite a bit of detail, and for the rest of the talk I have simplified it into this and divided it into 3 geographical zones with a proximal, transitional and a distal zone. I will now take you through a down dip journey. Basically, I will show you how the rocks look like. So in the proximal zone, the proximal zone is really dominated by fluvial channel fill deposits. So here you see single-story channel fill deposits, and they form a laterally continuous sheet throughout the proximal part of the study area, 10 to 15 meters thick. And then in the transitional zone, these are replaced by delta front deposits that are also very sand prone and have a tabular nature. You can see here that there's almost no pro-delta mudstone preserved, or maybe not deposited, which relates to the low accommodation, so the shallow water setting. We also find in this part of the study area these multi-story deposits. They're multilateral, multi-story, and they're bounded by this composite scour. And then if we move to the distal zone, we actually have more accommodation, so we have thicker mudstone pro-delta deposits. And you see here how they nicely grade into this sandy delta front deposits with on the top fluvial distributary channel deposits. And these fluvial distributary channel deposits are very common. They often form laterally amalgamated sheets of distributary channels. So this white line is the follows the channel base. The green line represents a maximum regressive surface, but this is less important for this talk. So they stack laterally rather than vertically, also as a consequence of the limited accommodation on the floodplain. And their infill is consistently sandy and lacks any marine influences. And again, we see this multi-story channel deposits. Here you see delta front pro-delta. So this composite surface separates the fully fluvial facies from the underlying deltaic deposits. And we interpret these multi-story channel deposits and the ones in the transitional zone as incised valleys, so related to drop in sea level, based on their regional occurrence and their multi-story multilateral infill and their estimated channel tops below the surrounding topographic surface. Okay, so we then can look at the complete profile. Here in brown again, the fluvial sandstones and how they are replaced basically by delta front sandstone. And if we then talk about surfaces, this regional surface below the fluvial channel deposits in the proximal zone would be the candidate for the sequence boundary back in the days. Then we have that surface below the distributary channel deposits that we named the basal distributary composite scour, and then the erosional composite scour bounding the incised valleys. And then there's one other concept that I want to introduce. This is the regional composite scour, which is the subaerial unconformity minus the interfluve as defined by Holbrook and Bhattacharya now almost 10 years ago, so it's not new. But we can nicely illustrate this concept based on our model, based on our outcrop data. So we'll take you through that step by step. So here we're going to build up the relative sea level cycle. Here you have the simplified profile, and here then the block diagram that is the depositional model, and you see the three zones: proximal, transitional, and distal. Brown are the fluvial deposits. These yellow ones are the delta front deposits. And then here in red, you see this discrete erosional surface at the base of the trunk channels, and then here in purple at the base of the distributary channels. So here at this first step, we have onset of deltaic deposition at the rim of the basin. Then the system progrades further into the basin, and you see how these discrete part of the erosional surface begin to amalgamate. Also, some of the earliest deltaic deposits are now eroded and cannibalized because there's such limited accumulation. Then there's the earliest sea level fall. There is coastal incision incision into the coastal prism, and these incised valleys begin to form. But there's also still activity and deposition by these trunk channels in the proximal zone. And then finally, there's earliest sea level rise. Part of the delta is still able to keep up, but eventually the delta plane is flooded. And what we see now is that this scour underneath these trunk channel deposits occurs at regional scale and was formed throughout this relative sea level cycle. And that's the concept of this regional composite scour, which forms continuous throughout a relative sea level cycle by the progradation of fluvial system. So how do we extend this surface into the marine realm? Well, there's different schools in sequence stratigraphy that tell you different ways of doing this, but the key thing that we have to keep in mind is that not the sediment that's not incorporated here basically feeds then the distributary channels and the clinothems that are genetically related. Another point that I want to make is that we infer active filling of channels rather than passive backfilling, and this is based on the fully fluvial infill of the different channel types, which implies that there's no complete bypass at any given time at any point, because there was ongoing deposition and erosion somewhere. And we can illustrate this in a different way with this Wheeler diagram. So here you see again the simplified profile. The numbers relate to these time steps, and then we have the relative sea level curve. So for instance, if we look at T1, we have here these fluvial trunk deposits, and the sediment that's not stored here feeds this clinothem here. So these are genetically related, and so are the discrete parts of the erosional surface at the base of these channels and these clinoform. Same here for T4, we have trunk deposits that feed these distributary channel deposits, and sediment that's not stored here will be stored basically in the clinothem deposit. And then when sea level starts to fall, a similar process happens here with these incised valleys. So the reshaping and formation of the valley walls and their infills occurs at step 5, 6, and 7, and is basically an ongoing process. And that makes this the individual segments of their tail and boundary surfaces.
2 minutes, Anna.
Yes, thanks. Are time equivalent to this discrete deltaic wedges, but also at the same time, sediment in the trunk channels is deposited in the proximal zone and forms this scour underneath. So in other words, the bypassing sediment feeds this time equivalent clinoforms downstream. This implies that this regional composite scour disperses into several surfaces, so we cannot have one correlative surface. Another important consequence from this is that we don't need a second sequence boundary to explain these incised valleys, and this has quite big implications for how we understand the basin infill, because using a second sequence boundary would imply a second drop in sea level fall. So I believe this concept evidences the need to focus on the dynamics and mechanisms of creating these surfaces rather than debating their nomenclature. And that brings me to the conclusions. Our study exemplifies that low accommodation systems form amalgamated sheet-like sandstone bodies. And it also highlighted the distribution of different channel types and their bounding surfaces that occur on regional and sub-regional scale. And the study also highlights the diachronous nature of the sequence boundary and suggests an alternative approach for extending the sequence boundary, or rather regional composite scour, into the marine realm. It disperses into several surfaces in the shallow marine part of the depositional system. And this has implications for how we understand the systems based in infill development, and also that there's no complete bypass, which might be influencing source to sink analysis. And finally, it's important that these dispersive surfaces can be facies boundaries between packages with potentially different reservoir qualities. So I think that rather than fighting over the name of these surfaces, we need to understand what we are mapping. And with that, I would like to thank you, and I take questions.
Yeah, that Wheeler diagram is killer, Anna. It's yeah, I love
Thank
that
you
figure. While we wait for some questions, do we have some hand risen? I have one question for you. Did you sample for your rocks for any other type of analysis, or?
Yes, we did. We actually have more than 300 samples, and we only used 5. I think the initial idea was to maybe do at one point a petrography study, and we also sampled for palynology, but it turned out that it had a very poor preservation quality. The 5 samples that we did use, you can use basically grain size to amongst others, calculate paleo slope. So we did that. Yeah.
Cool. So I see that we have a question from Arijit. And if I'm not mistaken, you are at Queen's University in Canada. Yeah, so he says, thank you for the great presentation. Isn't regressive surface of marine erosion to be considered in this context, or is that concept outdated?
Oh, the regressive surface of marine erosion. Well, I don't think the concept is outdated. It's just another one other surface. But well, I guess the regressive surface of marine erosion would be then one of these surfaces. Basically, it would be basically maybe this one here below, especially in the lower accommodation area. But yeah, I think then we have to really think of the original definitions, which is a bit of a, how do you say it? Use a trap in a way. Yeah, I'm not sure if this answers your question. Yeah.
No, yeah, I see what you mean. I think it's what you need to focus is what the surface means and the process involved, rather than just how you call it, right?
Yeah, exactly.
Yeah. So I don't know, maybe another question from, so this is a long dip surface pretty much, with little, so do you think, I mean, adding another level to this, how to correlate these surfaces? If Emma's got also a question, sorry Emma, but you have when you're at the rim of your fluvial belt, right? You might have just one channel that inside somewhere, right? You don't have a channel belt, so then you end up also having some isolated patches of surfaces, right?
Yeah, of course, if you include a strike sections as well, the more complete your recording, the more complicated it's going to be. I think if you would look at a map view, any of these surfaces will give you quite a complicated picture. Also, I think if you, for instance, think of this maximum regressive surface, which is really the turnaround from the progradation to the retrogradation, basically, if you consider that in map view, it's going to be quite complex in a way, because of the autogenic behavior of the system as well.
Yeah, this is great. This is awesome, Anna. Love it. Emma, do you want to go for it?
Yeah, Anna, that's a great talk, and I love that Wheeler diagram. It's really cool. Actually, the question I have is about that diagram. So I'm just wondering how you actually assigned your time steps to, you know, individual channels and size valleys, and then correlated to the decline of them that they fed.
Yeah, that's a very good question. In a way, it's conceptual, but the evidence that we have for this is that we infer that active infill of channel fill. So we know that they must have been actively filled, which means that there cannot be much bypass and not much passive infill. So from that, we basically infer that at any point some part of the system was being active, and hence we have continuous deposition throughout a sea level cycle, and from that basically involves this concept. But we don't have any proper evidence for dating individual channels. We cannot do that.
Okay, that's cool. Thank you.